Yeah, so we were discussing about calculation of position of center of mass for a continuous mass distribution by application of integration. Okay, so we saw that just like in case of discrete mass systems, we define the position of the center of mass like this. Okay. Summation mr divided by total mass. In case of continuous mass distributions, the summation is replaced with integration. So summation mr becomes integration RDM. Okay. And the denominator, which is summation m, becomes the total mass, or that can also be written as integration of dm. So basically summation is replaced with integration. Okay. And then we went on to see that continuous mass distributions can be divided into three categories: linear distributions, surface distributions, and volume distributions. So accordingly, for linear distributions, the differential mass dm becomes a length element, lambda dl. Okay. And for surface distributions, it becomes a surface element, sigma dA. And for volume distributions, it becomes a volume element, that is rho dV. Okay, and then we've gone on to see an example of application of integration in this kind of situation where we had a non-uniform rod.
So,
Yes.
left out the last part. Can you please show that?
Yeah, I'll show that, just a minute. Okay, so the example of this non-uniform rod is clear.
Yes, sir.
So we had this situation where the mass per unit length of the rod is like this, is given to us as a linear function of x. So we have to find the position of the center of mass. So one thing we can straight away guess by looking at the equation is that the center of mass will be to the right of the midpoint. That is, the x coordinate will be greater than 0.5 L, or in this case greater than 1 meter. But the question is by how much? And we also wanted to find the total mass. Okay, so this is where the application of integration comes in, that we take a differential section of the rod of thickness dx, right? So its mass becomes lambda dl, where lambda is this variable quantity. So we replace lambda with this linear function over here, this one. Okay, and we replace dl with dx. Okay, and then on the basis of that, we have the total mass as the integration of dm, integration done from x equal to 0 to x equal to L. So completing this integration gives us this value, okay, 3 by 2 lambda naught L, okay, which in this case comes out to be 3 kgs. And the position of the center of mass, that is now given by this formula. Integration x dm, that summation mx that we had for discrete particle system, is replaced with integration of x dm divided by this total mass that we've calculated above. Okay, so now x dm is again replaced with lambda into dl, and lambda is replaced with this variable formula that we have over here, lambda naught 1 plus x by L, and dl is replaced with dx. So this integration results in this quantity. The numerator is this quantity lambda naught into L square into 5/6 divided by M, where M is the total mass. Now we replace the value of total mass from here, which we had seen parametrically was this much. Okay. So this total mass is now replaced over here. So that gives us the final formula that in terms of L, it is 5/9 L. So 5/9 you can see is a great quantity which is greater than half. 5/10 is half, so 5/9 is greater than half. Okay, so definitely as expected, center of mass is to the right of the origin. Okay. Okay, then we came to this final problem yesterday. Let's review this one. And this is one of the standard examples. Oh, this is one of the two final problems. Okay. So we wanted to find the position of center of mass of a thin uniform. You can say it's like a thin wire which is bent into a semicircular arc. So we wanted to find the position of the center of mass of this semicircular arc. So now for this, we use a particular trick. And that is, so again, it's yeah. So when we slice the semicircular arc into differential length elements, DL. So you can see any particular length element DL, it is located at an angular position theta, and that length element DL itself will be subtending a small angle d theta. Okay, so our DL will become r d theta. Okay, so that was the trick for integrating over the surface that was the trick for integrating over this over the length of a circular arc, that we replace DL with r d theta, and that DL is located at an angular position theta. Okay. So now to find the y coordinate of the center of mass, because we know the y axis is the axis of symmetry, okay, that we've already understood here, that the y axis is the axis of symmetry. So the center of mass lies on the y axis. Okay. So now the y coordinate of the center of mass is given by this relation, integration y dm divided by total mass. Okay. So now that dm is once again lambda into dl, where lambda will become m upon pi r because it's a uniform distribution of mass, and dl is replaced with r d theta. Okay. And accordingly we get this calculation. Okay. Now from this, we moved on to the problem of center of mass of a semi-disk. Okay, which is an example of a volume distribution now.
The area, right?
Yeah, sorry, it's a surface distribution. Yeah, area distribution or surface distribution. So the method we chose to find the center of mass of this surface area is to slice it into semi-rings, which you can see over here in this diagram below. Okay. So this is the section you wanted to note down, right?
So even the part is about that.
Okay.
From semicircular disc only. Yeah.
Semi-ring from that part.
No,
Or
no, no. Disc only.
okay. So just go ahead and write this down. We'll discuss. Okay, finished with this?
1 minute.
Okay. Yes, I'll scroll down, Bhavika. So finish writing down this part.
Yes, sir.
Okay. Okay, done with this, people?
Yes, sir.
Okay. So let's look at some more examples of center of mass calculation, position of center of mass calculation using integration. Okay, so now next we will look at an example. Just a moment, I'll share the screen. So we will look at an example which involves a non-laminar surface. So what we mean by non-laminar surface is that the surface is not on a two-dimensional plane. It's curved over a three-dimensional space, that kind of situation. So for that, we will look at the example. In fact, what we can do is we can start with an example of a volume distribution. So for that, we will look at center of mass of a solid hemisphere. Okay. Okay. So let's look at this example next. The center of mass of a solid hemisphere. Okay, so imagine this is the diagram of a sphere that we have cut in half. Okay, and the center of that, the center of curvature of the original sphere, that is where we have taken our origin. Okay, and the plane that we have used to cut it in half, that is your xz plane, right? So again, y-axis is the axis of symmetry. Okay, okay, so the y-axis here is the axis of symmetry. And the xz plane is where the base of that solid hemisphere is lying. Origin is the center of curvature. So this is an example of what we call a volume distribution. Okay, so when we calculate the position of the center of mass using this formula here, ycm is equal to integration ydm divided by total mass. Okay, this formula over here. So what we see is dm is going to be rho dv over here. That means it is a volume element. Okay, now what kind of volume element we are going to slice over here? We're going to slice a thin disc. Okay, so as you can see on the diagram on the left, if we slice this hemisphere into thin discs, using a plane parallel to the XZ plane. So each disc we can say is the center of the disc is at a position Y with respect to our origin. The thickness of the disc is dy, and the radius of that particular disc is small r, whereas capital R is the radius of the whole hemisphere. Okay. So imagine a thin disc like this whose radius is small r and thickness is dy. So what will be the volume of this disc? The volume will be pi r square into dy. Okay. So now the mass of that thin disk dm is going to be density rho into the volume dv. So the density of the hemisphere will be how much? Total mass divided by total volume. So m upon 2 by 3 pi r cube.
Yes, sir.
Okay. So now we want to replace this quantity y dm, where dm will be replaced with rho into dv. So next step, we multiply the density rho, which is this quantity m divided by 2 by 3 pi r cube. So it becomes 3m upon 2 pi r cube. So rho into dv. Now dv was the volume of that thin disk, okay, which was pi into small r square into dy. Now, when we write the volume as pi into small r square into dy, which I've shown here, you can see that r, small r, is varying with y, and we're going to do the integration with respect to dy. So we want to replace small r in terms of y. So next step, what we do here is we understand the relation between small r, that is the radius of the disk, and y, the position of the disk from the origin. And that comes from Pythagoras theorem. So r square becomes capital R square minus y square. So capital R square is a constant, so no problem with that. Okay. So we express dv, that is the volume of the disk, purely in terms of the variable y, so that we can complete the integration. And of course, density is constant. Okay, so constant density into this dv, that becomes our dm, which becomes this final expression here, which is written over here. Okay, so people, are you clear up to this step where we have replaced dm as this quantity rho into dv?
Yes, sir.
So that becomes, so when we multiply these two quantities, rho into dv, you can see the pi will cancel. So we get 3m upon 2 r cube into capital R square minus y square dy. Okay. So once we've written dm in terms of rho dv, which is this function of y multiplied by dy. So once we do that, now we want to substitute this dm in the formula for position of center of mass, which is ycm is equal to integration y dm divided by total mass. So in this, what is dm? It is the mass of that thin disk, which we'll replace with this quantity, rho dv. But what is y? Y is the y coordinate of the thin disk center of mass. You're understanding the point?
Yes, sir.
Yes, sir.
So where is the y coordinate of the disk center of mass? It is at y itself, no? Because y is the distance that we've taken of the center of the disk with respect to our origin. So in our whole equation, y itself is the position of the disk center of mass. So we'll just replace, we'll just let y be, and replace dm with this quantity, which is rho into dv. which is 3m upon 2r cube, this term. Okay. So now the limits of integration, on replacing this, what will be the limits of integration? We are going from the largest disk, which is right at the bottom, to literally a dot size, very small disk on top of the hemisphere. So the range of y is from 0 to capital R to cover all the disks that we have sliced. So the limits of integration becomes from y equal to 0 to y equal to capital R. Okay. So substitute those limits, calculate the integral above. Okay, so for that you take all the constants outside and you're left with this type of cubic function. So integrate that from 0 to capital R, and of course divide the whole expression by capital M. Okay. So this integration is nothing difficult. It's just, some constant into y. So y's integration is y square by 2 minus y cube. Y cube's integration becomes y to the power 4 by 4. So in that expression now put the limits 0 to capital R. So on final calculation, the position of the center of mass comes out to be 3r by 8. So now again, this is one of the standard formulae that you have to remember for position of center of mass. Okay. So just make a note of this integration. And so far the three formulae that you've seen, center of mass of semi-ring, center of mass of semi-disk, and center of mass of solid hemisphere. These are these formulae. Yesterday we saw these two, semi-ring and semi-disk. So now to that table of formulae that you're making, you can add the solid hemispheres.
Yes.
Okay. Now, beside this integration, I've also shown you over here how to calculate the volume of a sphere using integration. This formula of volume of a sphere 4 by 3 pi r cube, which you might have learned in class 9th or 10th somewhere. Where does this formula come from? So one way to prove this formula or one way to derive this formula is using integration. So just like we have sliced the hemisphere into disks, here I've taken a solid sphere and sliced it into disks. Okay. So the volume of a disk is pi r square dy, where small r is again that, square root of capital R square minus y square. So we can directly integrate the volume of these disks. Okay. Integration of dv to calculate the total volume of the sphere. And the difference is when we have the full sphere, then our y is going from minus r to capital R instead of 0 to r. Or you can also do the limits from 0 to r to calculate volume of hemisphere, and then just double that. That will give you the volume of sphere. So this integration nicely shows you one way to demonstrate why the volume of a sphere is 4 by 3 pi r cube, or hemisphere's volume is 2 by 3 pi r cube, a fact that we've already used in the center of mass calculation here. So you can make a quick note of this volume of sphere derivation also. Okay. Okay, people. So is this derivation clear?
Yes, sir. But 1 minute, sir, we are noting it down.
Okay. Yeah. So unfortunately, some hardware issue at my end, so my pen tablet is not working right now. So I'm just showing you these derivations from my master notes. Okay. I will send you the same PDF notes. Don't worry. Okay.
Okay, sir.
But make sure you understanding each of the steps. Okay. If any calculation or any step is not clear, just tell me. I will explain in detail.
Yes, sir.
Yeah. So for the limits in the integration, for the center of mass of the hemisphere, what we've done is, you can see in the diagram. Okay, you can see in the diagram that we are slicing it into discs. Okay, which are all along the y-axis. So to cover the entire mass of the of the hemisphere, which is the lowest position where the disk is located, it's at the base. So there the y coordinate is how much? Y equal to 0. Understood? Na?
Yes, sir.
And the uppermost position where the hemisphere basically ends, that will be a very small disk, almost like a dot size. Okay, as you slice it progressively, you will see the size of the discs is becoming smaller and smaller as you
Yes,
go
sir.
up. So the topmost disk is almost having 0 radius, or radius tending to 0. But where it is located, it is located from the origin at y equal to capital R.
Okay, understood, sir.
That's how we understood. Whereas, for example, when we are calculating the volume of the sphere on the small section which I've written on the right, no, we are slicing into disks, but the lowest one is at minus R and the uppermost one is at plus R. So here the limits are from minus R to plus R.
Yes, sir, understood.
Okay. Okay, is this finished now? Done?
Sir, copying the sphere part.
Okay. Okay, so understood this part of volume of sphere also?
Yes, sir.
Okay. Okay, done, right?
Yes, sir. Done.
Yes, sir.
Okay.
Done.
Okay. Okay, now next, before we come to another example, we will see an application question, a typical type of question. I'll just share that question of how you will find the position of center of mass in a JEE, typical JEE type of question using these formulae and using the principle of superposition. So I've told you the importance of learning the formulae, and this question will show you this. Okay. All right. So now, okay, this is the question coming up. Okay, so this is the diagram given for the question. Okay, that we have a structure like a frame that consists of like three sides of a square frame of dimension 10 centimeter by 10 centimeter, and the fourth horizontal side on top is missing, and in place of that we put a semicircular arc. Okay, now the semi arc is made of a different material, so its lambda is lambda 2, that is mass per unit length. Lambda 2 is 2 grams per centimeter, whereas the square frame below is made of a different material and its mass per unit length lambda 1 is 3 gram per centimeter. So this whole structure is like this. Okay, so we have to find the position of the center of mass of this whole structure with respect to the bottom left corner of the square, which we are taking as our origin. So the question is, you have find the position of the center of mass with respect to the origin O. Okay, that means we have to find the center of mass's coordinates x, cm and y, cm with respect to the origin being this point, which I've shown here below. Okay. So this is where you can use superposition. You can replace the semi arc with an equivalent mass located at the center of mass of the semi arc, and you can replace the square, or at least each side of the square, with an equivalent mass located at each of the midpoints of each of the three sides of the square. So it then becomes a 4-particle system. Okay, one particle replacing the semi arc and one particle replacing each of the three sides of the square. So you have 3 plus 1, 4 particles, and then you use the particle center of mass formula to find the equivalent system center of mass. So to be able to do this question fast enough, you have to remember the formula for position of center of mass of semi arc. You can't sit and derive that in the exam. It will just take too long for you to complete this problem then. So that's where the importance of remembering the formula comes in. Okay. So just try out this question. I will show you the solution and answer in a minute. Okay, so people made any progress with the question? You understanding how to solve?
It's a calculator. Just
Okay.
2 minutes.
Okay. So I'll just start with the approach over here. So I'll take the semi-rings mass as M2. Okay. So in my calculation, I've taken the semi-rings mass as M2. So its mass is how much? It's lambda into the total length of the semi-ring. So lambda is lambda 2, which you can see above is 2 gram per centimeter. And the length of the semi-ring is pi r. And the radius of the semi-ring here is L by 2. You can see it's 5 centimeters. Okay, because the diameter of the semi-ring is L, which is 10 centimeters. So that is how I've got this mass of the semi-ring as 10 pi. Okay. Now if I'm taking this point, the midpoint of, the center of curvature of the semi-ring, if I've taken that point as P, then the center of mass C2 of the semi-ring is at a distance D above. And that's where I'm using the formula that D is 2R by pi. And R is L by 2. So that's how I'm getting the formula for D as 10 by pi. So that's one thing. And then the other thing I've done here is I've taken the mass of each of the 3 rods which form the 3 sides of the square. I've taken each of them as M1. M1 is not the total mass of the square, but it's the mass of each side. So it is lambda 1 into L. So each side of the square I will replace with a particle of mass M1. And the entire semi-ring I'll replace with a particle of mass M2. So that's where this diagram now comes in. Just a moment. We share that. Yeah, so that's where this diagram comes in. On the XY plane, I'm replacing each of the 3 sides of the square with 3 particles of mass M1 each. And I'm replacing the semi-ring with a particle of mass M2. Okay, people, so are we clear with the calculation of this?
Yes, sir.
Yes, sir.
I'll just show you, confirm the answers. Okay. So x coordinate of the center of mass is obviously, like, you can understand that, the line bisecting this whole structure at the line which is basically x equal to 5 centimeters is a symmetry axis. So xcm will be 5 centimeters. We don't need to calculate that separately. YCM we are getting like this. Okay. So summation of my divided by total mass. So summation of my, you can see that two of these particles m1 are located at y equal to 5 centimeters. One is located at y equal to 0. So that has no contribution to the numerator. And the third one, which is the semi-ring, is located at m2. M2 is located at this position. So this position is how much? It will become L plus D. Okay. In the diagram on the left, you can see it is L plus D. So it is 10 centimeters plus 10 by pi. So that's how we are getting this m2 into 10 into 1 plus pi. So that's the numerator, and the denominator, the total mass, is 3m1 plus m2. So in the final answer, I've just approximated pi as 3.14. Okay, so this is an application example question. Now, next up, we will come back to this thing, center of mass using integration. And this time, the next derivation we'll do is again a standard derivation. So that means it will lead to a standard formulae. Okay, we'll see the thin hemispherical shell next. So this example you have written down, all of you people?
Yes, sir.
Yes,
Clear?
sir.
Okay, the final answer. Okay, so I'm just switching to another part of the notes. Okay, so next example we are seeing, it looks very similar to this previous example, but this time it's not a solid hemisphere. No, it's a hemispherical shell, an open hemispherical bowl, that kind of thing, thin hemispherical shell. So this is again a surface distribution, though the surface is not lying on a two-dimensional plane. So it is what we call a non-laminar surface. Okay, lamina, L-A-M-I-N-A, lamina refers to a two-dimensional plane. So the previous example of a surface distribution we had seen, which was a semi-disc, that was a laminar surface. But this is a non-laminar surface because the surface is kind of curved in 3 dimensions. Okay, so once again, we can see in our diagram that if we take our origin at the center of curvature and the plane of the, the open part of the hemispherical shell as our xz plane, then our y-axis becomes the symmetry axis. So the center of mass lies somewhere on the y-axis. Okay. So in the diagram below, you can see I have taken the direction of the y-axis downwards so that I get the coordinate of the center of mass as some positive YCM. In the second diagram below, I've just replaced the direction of the y-axis instead of upwards as downwards, because the origin is at the midpoint of the open surface. So the center of mass is somewhere below it on the y-axis. Okay. So once again, we slice it using a plane parallel to the xz plane. But this time when we slice, because it's a hollow shell, what kind of shape we are getting? We're getting rings. Instead of thin discs, we are getting rings. Okay. Now this is where one little technical point comes in, that when we consider a ring, okay, so just visualize this ring like a ribbon which is wrapped around the hemisphere at a point like this. Okay. So what is the thickness of the ribbon that we should take? So for that, just concentrate on this diagram in the middle where I've shown the ring. So in this diagram, you can see that the thickness of the ring will be this thickness dl, which is the thickness on the curved surface. Imagine that ribbon wrapped around the hemisphere. So the thickness of that ribbon will be on which surface? It will be on the spherical surface. Okay. So it is not going to be dy. The thickness will not be dy. It's going to be this dl, which is on the curved surface. Because dy is like a projection, or it is like a component of dl, which is along the y-axis. Are you understanding this point, people?
Yes, sir.
So we should not consider the thickness of that ribbon or that ring as dy. We should consider it as dl, because dy is smaller than dl. It is like the projection or the component of dl along the y-axis. Okay. So hence, when we are considering the area of a spherical surface and we slice it into rings, we always take the thickness as dl and not as dy. Whereas when we are considering a solid hemisphere, so we are slicing it into discs. There it was a different situation. The disk was a volume. So we had to consider the thickness of the disk as dy and not as dl. Okay. So that is one important point to remember when we are applying integration. The difference between integrating over the surface of a hemisphere versus over the volume of a sphere or volume of a hemisphere. Okay. So when we slice a volume into disks, the thickness should be taken as dy. Whereas when we slice a surface into rings, the thickness should be taken as dl. Okay. So the moment we take the thickness as dl, we understand that dl is r d theta, because that thickness dl is itself like a small arc on the hemispherical surface. So it will be subtending a small angle d theta. And here I have taken theta as the angle with respect to the y-axis. Okay, the angular position of this with respect to the y-axis. So now see the diagram in the middle. You can see that this particular ring that we have, it has a thickness dl, which is r d theta. It has a radius small r, which from trigonometry you can work out. Okay, that thickness, that radius is becoming r sine theta. Sorry, the radius is becoming r cos theta. Okay, but just understand here that I have taken theta with respect to the x-axis now, not with respect to the y-axis. Okay. So go with the theta which is there in the middle diagram. Okay, not with the theta which is there in the diagram on the left, because there I have taken theta with the y-axis. Take it with the x-axis theta. Okay. So if you take theta with the x-axis, you can see the radius of the ring is going to become r sine theta. Sorry, r cos theta. Capital R cos theta. That's small r. And the thickness dl is r d theta. Okay. So the area of the ring will become what? Circumference into thickness. So that is this next expression. 2 pi into small r into dl. So that becomes 2 pi r cos theta, because we'll replace small r with capital R cos theta and dl with r d theta. So the area of this ring becomes like this in terms of d theta. It becomes 2 pi r square cos theta d theta. Okay. So is this clear so far, people?
Yes, sir.
Okay. Just make a note up to this step first. Okay. Then we'll continue with the integration part. Don't worry about the sigma part in the end. I'll explain that again. Just understand up to this formula that dA is equal to 2 pi r square cos theta d theta. And note down this small section here that for the surface, we are integrating rings. So the thickness of the ring has to be taken as dl or r d theta, not as dy. Okay, so people, are you clear with this area of the semi-ring, dA part, up to this step?
So,
Okay, so now in this one, what we'll do is, before we come to center of mass, we will digress from this a little and we'll see how to calculate the area of a hemisphere. Surface area of a hemisphere, you know as a formula, right? It is 2 pi r square.
yes, sir.
So where does that formula come from? Like we had just calculated volume of a sphere previously. So let's look at this first, okay? The surface area of a hemisphere. So that will become integration of the surface area of all the rings, right?
Yes, sir.
So just now we had seen that dA for a ring is how much? It is 2 pi r square cos theta d theta. Now go back to the diagram and you will see that what limits we should take to cover the entire area of the hemisphere. Okay. So to cover the entire area of the hemisphere, we should take the ring starting from the one which is in the xz plane. So that is the topmost ring for which theta will be 0. Because remember, theta we are taking according to the middle diagram. So theta is with the x-axis. So the topmost ring will have theta equal to 0. And going from that, we are covering up to the bottommost ring, which is like the dot over here of very small radius. So that one will have theta equal to how much? 90 degrees, pi by 2. Okay. So to cover all the rings that, you know, that together make up your hemispherical shell, we have to take theta from 0 to pi by 2. Okay. So just take down this derivation on the right first to understand the area of the hemisphere. You know, why it comes out to be 2 pi r square. The surface area of a hemisphere, or you can just double that for surface area of a sphere, so that all too familiar formula that surface area is 4 pi r square for a sphere, that can be demonstrated, that formula can be demonstrated by integration application again. Okay. So integration of cos theta is sine theta, as you know. So put the limit 0 to pi by 2. So upper limit is 1, lower limit is 0. Okay, sine pi by 2 minus sine 0, that gives you 1. Very simple way to show why the surface area of a sphere is 4 pi r square or hemisphere is 2 pi r square. Okay, so we'll come back to center of mass first. Just note down the derivation of surface area of hemisphere. Okay, so this is clear. Surface area of hemisphere. People written this down.
Yes, sir. 1 minute.
Yes. Okay. Okay. Just finish this, then we'll discuss further.
So done.
Okay.
So can you show the red part also?
Yeah. Yeah, Bhavik, I'll show you that section also. Okay. So let's come back to this thing now. So the area of the semi-ring, sorry, the area of the ring, how we had got, the area is the thickness multiplied by circumference. Nice. Just imagine a ribbon of length L, which we have wrapped around, okay, to form that ring. So that ribbon's length is nothing but the circumference. So that's 2 pi into small r. And the thickness of that ring is dl. So the area of the ring, again on the leftmost you can see, is dA is 2 pi r dl, where small r will be replaced with capital R cos theta, which you can see trigonometry wise in the middle diagram. The relationship between the radius of the hemisphere, which is capital R, and the radius of the ring small r is coming from theta. Cos theta is based upon hypotenuse. So from that, small r is equal to capital R cos theta. And of course, the thickness dl is r d theta. So that's how dA is coming as 2 pi r square cos theta d theta.
Yes, sir.
Okay. So that we used over here. Okay. And again, in this section, I was just explaining that why, when we are considering the surface area of a sphere or hemisphere, we should slice it into rings which are of thickness dl and not dy. Okay. Because dy is less than dl. Okay. So these two things are clear now.
Yes, sir.
Okay, so now let's come back to center of mass. Okay, so remember we have to find the y coordinate of the center of mass. So ultimately we have to use this formula below. Now that ycm is integration y dm divided by total mass. So far, how far we have come to? We have reached this position where the area, the differential area dA, we have written in terms of d theta. Okay, so now from this dA, we have to calculate what? dm, which is the mass of that ring. So mass of the ring will be what? Sigma mass per unit area multiplied by area of the ring, which is dA. Okay. So just now we saw that total surface area is 2 pi r square. So what will be mass per unit area? It will be m divided by 2 pi r square. So next for dm, we replace sigma with m upon 2 pi r square. So now we can substitute sigma into dA as sigma is m upon 2 pi r square into dA, which we've just seen is 2 pi r square cos theta d theta. So we get a very simple expression for the mass of the ring. dm is capital M into cos theta d theta.
Yes, sir.
Okay. So you can see, for example, the ring which is right at the top, for that theta is equal to 0. So its mass is m d theta. So it's comparatively a large mass. A ring which is somewhere in the middle, let's say theta is equal to 45, its mass will be less because it will be m by root 2 into d theta in comparison. And the ring which is at the bottommost position, which is almost tending to become like a dot, so its mass is tending to 0 because theta is 90 degrees at that position. So cos 90 is 0. So even the rings, they have a range of mass because they are becoming smaller and smaller as you go down. Okay. So next, once we got dm, now we come to the main formula of the center of mass, that ycm for the hemisphere is integration y dm divided by total mass. So in this integration, what is this y over here? Inside the integration, what should this y be? It should be where this mass dm is located, right?
Yes.
Yes, sir, from the origin.
So dm is the ring. So what is y? It is the y coordinate of the ring center of mass, right?
Yes, sir.
So again, in the diagram, see what is the y coordinate of the ring center of mass? It is this distance from the origin to the center of the ring. So that is the
Yes, sir.
perpendicular for this triangle, right? For this right angle triangle, y is nothing but the perpendicular. So it becomes capital R sine theta. So that is why we replace the position of the ring center as y equal to capital R sine theta, right?
Yes, sir.
Yes.
Okay. So now replace these two terms in the integration, y as capital R sine theta and dm, which we have written as m cos theta d theta. And once again, the limits are simple. We are going from theta equal to 0 to theta equal to 90 or pi by 2, because we are going from the topmost ring for which theta is 0 to the bottommost ring where theta is 90 degrees. So now this integration has to be done. Okay. So this integration, there are actually two ways of doing it. I have shown you one method here, which is called the substitution method. You can do another method, which is a formula based method. sine theta cos theta can be written as sine 2 theta by 2, right?
Yes, sir.
So you can take the half outside and write it as integration of sine 2 theta and do it that way also. Whereas I have done it by the substitution method, which I've shown you over here. So it's integration of sine theta into cos theta into d theta. Now you notice that cos theta is the derivative of sine theta. So if you replace sine theta as a dummy variable z, then cos theta d theta becomes dz. So that's why I've used this substitution method. So just take down the integration finally. And then the standard formula that we get from this, that the hemisphere center of mass is in fact at the midpoint. It is at capital R by 2 when you complete this integration. So just go over the steps of the integration very carefully, the substitution, the integration, and finally the limits and how we get this formula. The integration will give us half, so it's R by 2. Okay, people, so is the integration clear?
Yes, sir.
Okay. So I've done it by the substitution method. You can also try the other method which I told you, that you can, instead of substitution, you can replace sine theta into cos theta as sine 2 theta by 2, and then take the half outside and directly do the integration. Okay. Okay, so we've almost completed the standard formulae for center of mass. Okay, so I'll just list out the ones examples we've seen. The only one remaining now is the solid cone. Okay, position of center of mass of cone. That will complete your list of standard formulae. Okay, so once again, I'm repeating, while the derivations are important for your understanding of application of calculus, but it's also very important that you memorize the standard formulae. Okay, for the type of question that I just showed you, that semi ring with the three sides of the square one, those type of formula, those type of questions are pretty common at JEE level, and you have to remember the formula, because otherwise it will just become too lengthy. Okay. So semi ring, semi disc, right? Hollow hemisphere, solid hemisphere. These are four of the standard formulae. Okay, so semi ring was 2r by pi, semi disc was 4r by 3 pi, solid hemisphere was 3r by 8, and hollow hemispherical shell, as you see, is r by 2. Okay, so to this list you have to add the solid cone. Okay, now derivation of solid cone center of mass will be very much like we have done the solid hemisphere. You slice it into rings. Okay, by cutting with an axis, cutting by a plane which is parallel to the axis. So I will leave that derivation as a homework problem for you. Okay, and we'll discuss it in our next lecture. So just you can write down in your notes over here, do the derivation of center of mass of a solid cone yourself. You will find it in some standard reference books also, but try to do the derivation yourself. We'll discuss the method in the next lecture. Okay.
Okay, sir.
Now let's come to an additional formula, which is especially for JEE Advanced. You can add it to your list of formulae. If we have this situation, let's write down the formula first, then I'll show you the derivation. Or in fact, this derivation also you can try yourself, that instead of full this thing, a full semi ring, if I have a wire which is bent into an arc shape, okay, this one. So the red colored line over here, this red colored arc, this is actually our mass. Imagine it's a thin wire which we have bent into the shape of an arc, which is subtending a total angle of alpha at the center of curvature O. Okay, so for example, if alpha becomes pi, we are talking about a semi ring. If alpha is pi by 2, we are talking about a quarter ring, that kind of situation. So we want to find the position of the center of mass of this arc. Okay, so you can just write down the heading over here, which is missing, that center of mass of a thin uniform arc. Okay, instead of thin uniform semi ring, it's just a thin uniform arc. Okay, center of mass of a thin uniform arc. So the radius of that arc is capital R, and the angle it is subtending at the center is alpha. So once again, you can see that if you look at the angular bisector, which I've taken as my y-axis over here. So the y-axis is bisecting this angle alpha into two equal halves, alpha by 2 and alpha by 2. So that is the symmetry axis. Okay. So because that is the symmetry axis, the center of mass lies on that axis at a y coordinate, which is given by this formula, integration y dm divided by total mass. Okay. So the method of derivation is very similar to how we done for the semi ring yesterday. Okay. Only thing that changes is the limits. In the integration, the limits for theta for semi ring were from minus pi by 2 to plus pi by 2. You just go over your notes, you can see it's minus pi by 2 to plus pi by 2. Here it is replaced with minus alpha by 2 to plus alpha by 2. So that will give us this formula, which is again a sort of standard formula which you can memorize. Okay, that for any general arc, it is r sine alpha by 2 divided by alpha by 2. Okay. So for example, if we are talking about a quarter arc, then we should replace alpha with pi by 2. So it will become r sine pi by 2 divided by 2. So that is r sine pi by 4 divided by pi by 4. So pi by 4 is 45 degrees. So that's how we are getting the 1 by root 2. Okay, one thing you should remember while applying this formula is remember to take alpha in radians. You should not take alpha in degrees. Okay. You should take alpha in radians. So this is an additional formula that you can add to the list, okay, especially for JEE Advanced. So people, this last week, have you had any physical lectures or all the lectures have been online only?
Sir, all of them.
The coming week, hopefully some physical lectures will also start. You had at least some doubt sessions, right?
No, we only had online.
Okay, probably because of school restrictions or whatever. But we are expecting like first week of February, we will have at least few doubt sessions offline, if not half the lectures offline again. And then we are expecting probably by second half of February, we'll go to a situation where we're completely offline. All lectures will be offline. What about school? You were having lectures in January or lectures were suspended?
No, we were having online lectures.
Online only, no? No offline lectures in Jan.
We are having internal tests and offline exams from February 14th.
Yeah, sir.
Okay. So then you can expect that after your internal tests are over, when we resume, probably, hopefully, like if everything goes all right, we'll have a situation where we are back to pre-COVID normal situation.
Those tests are running till March 11th.
Okay. 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 Now we can do this next as an application question. Okay. That we want to find. So I'll bring you to the solution later. Okay. Try this as a question now. That we want to find the position of center of mass of a quarter disk. Okay. We had seen semi-disk earlier. Now use the same method for the quarter disk. Slice the quarter disk into quarter arcs. Okay. So just try to formulate the solution of this question first yourself. Make a diagram where you sliced it into quarter arcs, and also make the symmetry axis and all that. You'll see the angular bisector, which is cutting this 90-degree angle into 45, 45. That is the symmetry axis. So your center of mass will definitely lie on that axis. Okay. So set up the question yourself. I'll show you the solution in a minute. So what is the physics syllabus for your upcoming test in February, your school test?
No,
Oscillations and waves, then thermodynamics.
Okay. So oscillations and waves has been covered in your school lectures?
Yes, sir.
Yeah.
It has been.
And you're using NCRT as the reference for that, or
So ISC book.
sorry, your ISC. So you're using the ISC textbook? Yeah.
Yes.
Yeah.
What is the name of the author of your ISC textbook currently?
So once again, I'll just check in.
Yeah.
Sir, it's Kumar Mittal.
Kumar Mittal. Okay. One time it used to be a book called Nelcom and Parker, but I think it has changed in the last 5-6 years at least. Anyway, so go through oscillations and waves from Kumar and Mittal carefully. If there are any basic doubts about formulae or definitions and all, you can send that to me over WhatsApp or text also. I'll help you with those things also. Because it will take some time before we come to oscillations and waves in our JEE syllabus. So for the moment, just do the basics, the definition and basic formula and all that from your textbook.
Okay.
Okay, so have you set up the integration for this? Should be something like this diagram below. Take your y-axis as the angular bisector. Okay, very good, Bhavika. I'll show you the answer. Yes. Okay. So now you slice a quarter ring. So quarter ring of, let's say, radius small r and thickness dr. Okay. So again, you can replace the mass of that ring as sigma dA. Okay. So your sigma will be total mass upon total area. So that is capital M by pi r square by 4. So that's how I'm getting this 4m upon pi r square into the area of that quarter ring. So the area of the quarter ring is how much? 1/4 of the circumference. So pi r by 2 into dr. Length into thickness. So length is pi r by 2 into thickness, which is dr. So that's how we are getting this term. So dm is this now. Okay, dm is this much. Okay. Now this is where this above formula comes in. So this thin green colored ring that we've taken, this thin differential ring, where is its center of mass located? Its center of mass is located at this y coordinate, which is given by this formula. Okay, r sine alpha by 2 divided by alpha by 2, where alpha is nothing but pi by 2. So it becomes this. Okay, 2 root 2 r divided by pi. Only we'll replace capital R with small r now, because that ring has a radius of small r. So the center of mass of that quarter ring is located at this y coordinate. So now for the center of mass of the entire quarter disk, we have to integrate y dm divided by total mass. So y we will replace with this 2 root 2 r by pi, and dm will replace with this quantity, sigma dA, which was this much. And once again, we are going from r equal to 0, like the dot shaped very small quarter ring over here, right up to the one at the outer circumference, which is capital R. So limits are 0 to capital R. So now you have to just complete this integration. So this is where I have made use of that formula for general formula for center of mass of a thin arc. So in that I've replaced alpha as pi by 2 for this for the quarter circular arc. Okay. And I've made use of that in this derivation. Okay. So try to do this integration yourself and match the answer. You should be getting what I've written in the end over here. Okay, people, so we are clear with this question?
Yes, sir.
Okay. So now, so this finishes the center of mass part for us. Okay. Here I've shown you an alternate method of doing this. Okay, I'll send that to you in the notes. I mean, there are a couple of alternate methods. One is you can also take, you know, thin triangles like this, but then you'll have to use center of mass of triangle. Or you can also cut it into horizontal strips instead of cutting it into horizontal or vertical, whatever be the case. Okay, you can do it that way also. So these are some of the other methods you can try out. So I'll send that to you in the notes. Okay, now, so this completes the center of mass by integration method. Only remember that you have to do the derivation of this one yourself, the cone. Okay, so do that and I'll verify that derivation for you in the next lecture. Now I want to do one example question based on collisions, because the most important part of this chapter is collisions. And of course, we still have to do variable mass system. Okay, so we're not done with the chapter. We have to still do variable mass systems, which I'll discuss in the next lecture, because that I would like to finish off the whole thing in one lecture, variable mass system. So now I want to discuss another example problem in collisions. Okay, just a moment, the question coming up for you. So this example is kind of to do with collision of a particle with a surface. Very typical type of question at the JEE level. So I'll just put up the question, you try it yourself first, then we'll discuss. Okay. So it's a numerical problem, it will give you some practice also. Okay. So this is the question now. So it says that what we are doing is a particle is dropped from a certain height given to you. So it's dropped from this position onto a inclined plane. So it makes an oblique collision with the inclined plane because it will fall vertically. So it will have an oblique angle. So now the question is telling us that it's observed that immediately after the collision, the particle has a horizontal velocity. So it impacts that surface and gets projected from that surface, but with a horizontal velocity. So that part is given in the question. Okay. When we drop it from a height of 20 meters, okay, it makes an oblique collision such that just after impact, the velocity v is horizontal. So from this information, we have to find how much that magnitude of that v is and what is the coefficient of restitution for this. So just try out this question on your own. I'll give you a couple of hints in some time and then we'll discuss the solution. Okay.
Sir?
Yes.
So the height 20 meters is measured from the ground or from the incline?
No, from where we have dropped it. I mean, from where it will impact. Okay.
Okay,
So
sir.
from where we have dropped to where it impacts on the surface, that height is 20 meters. Okay.
Okay, sir.
So it's in free fall for 20 meters and then it makes the impact like that. Okay.
Yes, sir.
Okay, so anybody got the value of V?
15 meter per second.
Very good. 15 meters per second is correct. So first of all, the concept we will use in this question is this, that, when there is an oblique collision, the impact velocity is tangential component, and the velocity after impact, the tangential component, they are the same. There is conservation of tangential component of momentum. Okay. So in this diagram, which is different from the above one, but V sine phi is equal to V naught sine theta, whereas the separation velocity is the normal component, so it's V cos phi. The approach velocity is the normal component, which is V naught cos theta. So the relationship between separation velocity and approach velocity comes from coefficient of restitution. So these two concepts have to be used over here. So in the above question, you can see that free fall through a height of 20 meters means the impact velocity will be root 2 gh, or 20 meters per second, right?
Yes, sir.
So if the impact velocity is 20 meters per second or V naught, and the inclination angle is theta like this, then what is the approach velocity? It is a normal component. So it is V naught cos theta. So here our approach velocity is 16. And our tangential component of velocity is the sine component. So it is 12. Okay. So this is the situation just before impact. Now we will compare this situation to the situation just after impact. And that we will see is like this. If just after impact, the velocity is horizontal and is equal to V. So you can see what is the tangential component. Now it is V cos theta, or it is 4 by 5 V. And what is the normal component? It is V sine theta. So it's 3 by 5 V. So that is the separation velocity. So now we'll use each of these formulae. That separation velocity is E times approach velocity. So 3 by 5 V should be equal to E into 16 from above, whereas tangential component is conserved. So this V cos theta, that should be equal to 12. So from that, I guess you would have got V as 15, right? This is the same method you used?
Yes, sir.
Very good. And now you just replace this value of V in the above formula, and you will get the coefficient of restitution. And as expected, you can see because V is less than V naught, there is loss of kinetic energy, which means that E should be less than 1. And that is what we've got, 9 by 16.
Yes, sir. I got the same.
Got the same? Yes. Okay. So these type of questions are the most common questions at JEE level, the collision type of questions, or conservation of linear momentum, or other examples where we've seen that energy conservation and momentum conservation both apply, like those spring mass type of systems, etc. So these are the most common type of questions, high frequency questions in JEE. Then there are every now and then few questions based on the position of center of mass by superposition or integration also. So that part is also important. Okay, but less frequent. The maximum target questions are these things: conservation of linear momentum and especially collisions. Okay, so as I said, now we're almost done with center of mass. One more lecture remaining for the theory of variable mass system, including rocket propulsion system. So that will be one of the lectures in the coming week. And probably we'll take one more lecture to complete problems and doubts and all that. So please look at completing HC Verma and maximum questions from your module also. I'll be sending the answer key to the module also very soon. Okay. Okay, people. So hope you understood this question, all of you.
Yes, sir.
That's it for today's session. Okay. Let's see. Hopefully this week we will have one of the offline sessions also. Okay. And that's it for today's session. Have a nice day, people.
So,
Yes, beta.
could you please scroll up for just a second? I want to check if I have done it right.
Yeah. Okay. So the solution of this question is here only. Okay. The concept is above over here, which I've written. Okay. You want to check the data of the question, or?
Yeah, data only, sir.
Yeah. So H is 20 meters. Okay. And theta was 37 degrees.
Yes, sir. Done.
Done? Okay.
Yeah.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay. Bye.
Thank you.
Bye, sir.